Alright, so I'm going to prove the fundamental theorem of algebra here. This is a request from a Twitter friend, and I've always kind of thought it would be fun to prove this in a video. So it's going to be a no-nonsense proof, and what I mean by that is that it's not going to use, there's a lot of ways to prove the fundamental theorem of algebra. Most of them involve some pretty fancy machinery from, like a graduate level complex analysis class. But you don't need any of that. You can actually just prove it all using some very basic facts that most people see depending on who you are, sometimes in high school, sometimes in undergrad, but definitely not past that. I've written the ingredients down here, but let me just read it off. And this is going to be a little off the cuff. I just kind of wanted to exercise my teacher mode a bit and do a cool proof. Here, just in case you forgot, the fundamental theorem of algebra says if you have a degree n polynomial, it always has n complex roots, counting multiplicity. So that means it could have the it's a little cheap, essentially. You could have the same root 3 times. It might count for 3, but you are going to have n in terms of you'll see why, kind of. I mean, I think when people learn this stuff, they see this multiplicity thing and they're like, that's kind of stupid, that's cheating. But you'll see why it comes up. Furthermore, if you've got a polynomial p of z and its degree n, and z1 through zn are its roots, then p can be calculated as this. You could just write it down this way. Yeah. So, this big pi here means product. So this is z minus z1 times z minus z2. It's just the classic factoring thing that you've seen. Okay, so what are the basic things? I'm sure most people know what this is. We need 3 basic ingredients to do this proof. You need Euler's formula, which I'm guessing the person that asked me for this is familiar enough with complex numbers that they would. I'm sure nobody would ask to see a proof of the fundamental theorem of algebra if they weren't like just a little bit familiar with complex numbers, because this word complex here is essential. This is not a true theorem if you don't include complex numbers, and a complex number is a number of the form a plus ib. It's essentially a vector. You've got 2 dimensions now instead of 1. You can go in the real direction, that's a, and you can go in the, in fact, I'm going to make this bigger because I do want to draw on it in a second. So you can go a in this direction, and then b in this direction, and then you get a point here, a plus ib. You treat it as a single number, but it's essentially a vector. And so Euler's identity is essentially a requirement for how the exponential function has to behave on imaginary inputs. And Euler's formula gives us that on imaginary inputs, what e to the on a purely imaginary input, you're limited to just being on the unit circle in the complex plane. So essentially what this says is that, because cosine plus I sine, cosine is the x parameter of the unit circle, sine is the y parameter. So really this is just a point on the unit circle in the complex plane, and e to the I theta has to be on that. So you're just basically, by increasing this theta here, you're just kind of rotating around. And the reason that we need that, we don't really need that, but it's very helpful, because what it means is that you can write any complex numbers in this really nifty form. So, of course, you can specify a complex number in like rectangular coordinates, which is what I did here. It's called rectangular because I have to kind of specify a rectangle to give you this point. I go this far in this direction, and then this far in this direction, right? But you could also specify it differently. I can say go this far at this angle. Right, I could just say that. Go this far at this angle. And that, I still need to specify 2 numbers, but now I'm specifying an r and a theta. And the r is greater than 0. It's a real number. And theta is an angle between 0 and 2 pi. And you can use that to specify any number in 2 dimensions. And normally, if I didn't have Euler's identity, I'd have to write this as like z equals a plus ib. Or sorry, I would have to write this as like z is equal to r times cosine of theta plus I sine of theta, kind of to say where am I on the circle, and then how big is the circle I'm on. But I can just cross all this out and write e to the I theta, and that gives me a nice little compact way to write down arbitrary complex numbers, and that'll be helpful. So polar form for complex numbers is just a very compact way to write complex numbers. You can see this plus sign means trouble whenever you're trying to multiply two different complex numbers in rectangular coordinates. But if you write them down in polar, it's much easier. You don't have to FOIL. So we're going to use that quite a bit. And then the second one I put a star around because this is really the star of the show is the triangle inequality. The triangle inequality says that for all complex numbers x and y, that's what the C means. Everyone's seeing R is the real numbers, C is the complex numbers. But yeah, for all x, y, and c, the real triangle inequality is this. You've got that the sum of x plus y is less than or equal to this the value of x plus the value plus the magnitude of y. I'm gonna try to call the size of this like the absolute value. I'm never going to say the word absolute value in this except for just now. I am going to say magnitude, and I'm going to try not to say modulus, but I will accidentally say modulus a few times. Just a word that gets used for that, but it's just the magnitude. It's the absolute value. I should probably say this. So for, I guess I'll put this on the side. For a complex number z equal, and I'll just say z equals a plus I b. The magnitude of z is equal to the square root of a squared plus b squared. So it's just the magnitude of the vector in 2 dimensions. It's just the Euclidean distance from 0 is what this is. And so it's absolute. I mean, obviously this is equivalent to being the absolute value if z is a purely real number, right? If z just equals a, and plus I times 0, then the magnitude of z is just the square root of a squared, which is the absolute value of a. So for real numbers, this is just the extension of the absolute value function to complex numbers. You can think of it that way. But anyway, it's a distance function. It gives you a distance function. So maybe I should say this. The real triangle inequality is nothing I wrote here. The real triangle inequality, the reason it's called the triangle inequality, it's kind of weird to talk about this being the triangle inequality because it only has 2 numbers, x and y. If it's a triangle, shouldn't there be 3? And the answer is yes. The real triangle inequality says that the distance between x and y plus the distance between y and z is always greater than or equal to the distance between x and z. In other words, the shortest distance from x to z is always just the straight line. This means distance, but and that's the thing. The triangle inequality is like an essential component that you need to call something a distance function. And in our case, our distance function is the magnitude of z1 minus z2. If you take the magnitude of the difference between 2 numbers, you're going to get the distance between the 2 numbers. That's true for the real numbers too, right? A minus b, that's the distance between a and b. And that's true for complex numbers as well. And this distance function is a metric. And so because it's a metric, it satisfies this triangle inequality. And so because of that, you can easily get this thing, which is what most people consider to be the triangle inequality in terms of what they use a lot. How do you get that? Well, you just insert something. You say, okay, x plus y, well, that's equal to, pick your favorite z. Well, that's x minus z plus y. I just added 0. But then you put some parentheses around these guys. Whoops, I did not mean to, sorry, not x minus y. I meant to say distance between x and minus y I meant to put here. And I could put a 0 here. Okay, and then I can split that up. Okay, wait. I'm doing this backwards. Let me try again. Pick your favorite z and start with the thing on the left side here. Well, no, I guess you don't have to. Let me try that one again. X minus y is equal to x minus z plus z minus y. Put parentheses around these guys. And this is the distance between x and y. And so I know that that distance has to be less than or equal to the distance from x to z plus the distance from, I should have rehearsed this, from z to y. or from y to z, because obviously the distance is the same for both. And so this might not look like what you got, but just then pick z equals 0. So if z equals 0, then the distance between x and y is less than or equal to the magnitude of x plus the magnitude of y. And then if I just picked, minus y, then I would get that this is less than or equal to x plus minus y, and then I can just get rid of this because who cares? And so that gives you the triangle inequality that I wrote here, which is what we're going to use a lot. This other side of the whole thing, see if I could please erase this. This guy down here, this one on the left side, this is sometimes called the reverse triangle inequality. And it's a little more confusing to look at, and luckily we don't have to think about it too hard, we just need to use it a bit. But we are going to need both, the regular triangle inequality and its strange reverse counterpart. So the triangle inequality is going to do, honestly, 90% of the legwork for this proof. And the reason the triangle inequality makes sense, the reason it should be true in general, the reason, the triangle inequality in the sense that you normally state it as an axiom, the reason that should be true is because, just, think about it. If you've got, here's x and y, I want to get from x to y, what's this distance? Well, it's certainly bigger, it's certainly smaller than it would be to go from here to here, some z, and then go from there to there. That would be stupid. This wouldn't be a valid distance. You wouldn't have a valid notion of distance if for some reason going over here and then going over here covered less distance than just going from here to here. And you can see we're making a statement about a triangle here. And so that's why it's called the triangle inequality. Probably more information than anybody cares about, but, I'm trying to do this as much from scratch as possible. Obviously, I can't prove this right now. That would require some calculus. Not a lot, but some. And then finally, the extreme value theorem, which most people learn in Calc 1, but they don't understand it, and is actually quite a bit of work to prove in like a real analysis class, and you kind of have to reprove it in a complex class because it technically means something different. But what it means, it's a topological fact, really. What it means is that any continuous function has a maximum and a minimum over a closed bounded set. So if you have, like, the way that you treat it in Calc 1 is that if I have an interval from a to b, and I have a continuous function on this interval, then f has to have a maximum. F has a maximum and a min in a and b. And that might sound kind of silly, right? Like, of course the function has a maximum minimum. What would it look like for a function not to have a maximum minimum on some interval? But you've seen lots of functions that look like that. For example, take an asymptotic function that's approaching 0, it never gets there, right? But it only has the privilege of never getting there because the interval never really ends, because I'm really talking about like 0 to infinity here. So this function f, maybe I'll bound it at 1. So maybe I'll just say it like this. If I have a function, there's no maximum and no minimum on the interval from 0 to infinity, right? There is a max but no min on I mean, and the max and min, you could say they're infinity, right? But they, that would be stupid. I mean, infinity's not a number. So, I mean, what the bottom line is that you can get bigger and bigger, but you can never actually achieve the maximum, right? But if you kind of bound it here, then you do get a max but no min, and then if you bound it like here, then you do get a min, but now we're in some closed bounded interval. And so this is kind of the minimal requirements you need to have, like, to assume that you have a maximum and a minimum value. In complex, we have a whole, we don't have a number line to work with anymore. Instead, we have a plane. And so what we want to talk about are just closed bounded intervals like this. Just clear borders. If I have a continuous function that's continuous over this region, then it has to achieve, then I can't really say the function itself achieves a maximum and a minimum. For our purposes, I should say, Okay, have a complex function, let's say g of z. You can't really talk about big and smallness in complex land, because if you're spitting out complex numbers, they're not really ordered, right? Look on the complex plane. Is this number bigger than this number? I don't know. I mean, it's not really. They're just locations now. So you got to say something different. Instead, what you want to say is that I want to consider maxes and mins for the magnitude of g of z. This is a real number, and so I can talk about maxes and mins for it. And luckily, this guy here, this absolute value thing, this is a continuous function. This is a continuous function, and because of that, and so if g is continuous, then the magnitude of g is also a continuous function, and then you can revert to the extreme value theorem that you learn in Calc 1, and say that this is a continuous function, so it has to achieve a maximum or a minimum magnitude on this region. So that is something we're going to use. This is going to do a lot of the initial legwork for us. So these three things, I think, are everything that you need, aside from just some basic mathematical maturity, because this is a difficult proof. Not difficult, but it's not simple. I think it's a really good exercise to try to understand. But I think these three things are kind of what we really need to get started, or just do the whole thing. All right. So the plan. Let's write down the plan. So here is the plan. So step one, there's going to be 3 parts to this proof. Step one is we're going to start with something a little more humble. We're going to start with a polynomial. So start with a degree n polynomial. I'm going to call it P of z. We're talking about complex numbers. We're done with x's. Z is my new best friend. And I'm going to label it a0 plus a1, plus a1 z plus a2 z squared plus dot 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 plus a n z to the n. So here's my arbitrary polynomial. This is the guy we're going to focus on for the whole proof. All of these a's are complex numbers. Keep that in mind. And because it's degree n, specifically, degree n means that a sub n is non-zero. Specifically, this guy right here is non-zero. Otherwise, it wouldn't be a degree n polynomial. It would be a degree something smaller than a degree n polynomial. So by assuming it's a degree n polynomial, we are assuming we can write it this way, and that this last guy here is non-zero. That'll be important. So what are we going to do with this thing? Well, first we're going to show that it has a minimum. Show that it has a minimum that occurs at some z0. Oh, not, okay, sorry, not it. I gotta be careful, because this thing, again, this spits out complex numbers. I can only really talk about the magnitude of p. This thing, this real valued function, has a minimum, and that minimum is going to occur at p of at z0. So we know that, yeah. So we know the smallest thing that we can get here is going to be achieved somewhere, and then we're going to, once we have that, we're going to assume, by way of contradiction, that p of z0, the magnitude of it, is not 0, something bigger than 0. And then we're going to arrive at a contradiction, meaning that it has to be 0. Contradiction will mean that p of z0 has to equal 0, but that can only occur if and only if p of z0 is equal to 0. That's another property of the absolute value function. There's only one way to get 0 out of it, and that is if the thing inside of it is 0. And then we'll do the factoring. That'll just be kind of a finish off. That'll be the simple part. In fact, I might even... Well, okay, we'll do it in order. We'll go in order because that's the only thing that makes sense. Okay, so let's start with step 1. So this is kind of the main event. Step 2 here is going to take the longest. But step 1 isn't exactly that simple. You got to be a little careful. I'm sure, you know, for random people watching, this is going to seem the most kind of frivolous part, but it is important. Okay. So the way to make sense of this is to, and honestly, I'm going to use the triangle inequality so much that I'm just going to go ahead and start writing it. We need the reverse triangle inequality immediately, so I'm just going to go ahead and write it down for our memory. Magnitude of x minus y is less than or equal to the magnitude of x plus y, obviously, is less than or equal to the magnitude of x plus the magnitude of y. So this side is the reverse triangle inequality. This side is the regular triangle inequality. So what we're going to do is we're going to look at z, but we're going to look at its polar form. So pick any z. Pick any z. I guess I'm going to start part 1. So pick any z equals r e to the I theta such that r is greater than 1. I'm going to make sure I'm going to pick an r greater than 1, and we're going to see what happens. So to start off, we're just going to look at the polar form of. We're going to plug a polar form complex number into here and stare at it. Not even stare at it specifically. We're going to stare at the magnitude of the polynomial evaluated at z. So this is the magnitude of p of r e to the I theta. And so that's equal to a0 plus a1 r e to the I theta. That's just a1z plus a2. And now I have this whole thing squared. R e to the I theta squared. Just to kind of make this very clear, that's going to be r squared times e to the I 2 theta, right? And so that's what I'll write. R squared e to the I 2 theta plus dot 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 plus, and then just to kind of make this look better in a bit, I'm actually going to write the second to last term. A sub n minus 1 r to the n minus 1 e to the I n minus 1 theta plus a sub n r to the n e to the I n theta. Close brackets. So here's the thing. And so we are ready to do the first use of the triangle inequality, and that will come from putting parentheses around here all the way up to here, and then looking at this guy by himself. And so basically, I'm going to use the reverse triangle inequality here. I'm going to call this guy y, and then I'm going to call this guy x. And so by the reverse triangle inequality, this thing is greater than or equal to, we're going from here to here, or we're going from here to here, sorry, the magnitude of a sub n r to the n e to the I n theta minus all of this garbage. a0 plus a1 r e to the I theta plus a2. I'm not going to write the second one. So we got this. We've split it up that way, and you'll see why that's important in a moment. But before I do anything, I'm going to use the triangle inequality again, the other one. So now we're going to say goodbye reverse triangle inequality. Regular triangle inequality is my new best friend. And we're going to apply it to this big term over here that has all the other terms in it. Now, it might look like this is in the wrong direction because this is less than or equal to something. But if I replace this guy here, if I replace this whole term with something bigger, well, hold on. If I take this term and I replace it with something bigger, then now I'm subtracting away something bigger, so I have something smaller. So the whole thing is still bigger than. Let's go ahead and mess around with this. The magnitude of a sub n r to the n e to the I n theta. That's the I can kind of distribute the magnitude. So this is a sub n magnitude, r to the n magnitude, e to the I n theta magnitude. I'll deal with the rest of that in a minute. Minus, and then I can kind of put parentheses and say, okay, now I can take the magnitude of all of these guys. And before I do that, actually, I want to make sure that we understand this to simplify what I have to write. There's nothing I can do to a sub n by just besides just leaving it in brackets. This r to the n, though, is just r to the n. I don't need brackets around it because r is a positive real number. And then this thing here, this is just 1. E to the I n theta, that is just some location on the unit circle, the circle of radius 1, the circle of distance 1 from the origin. This is the distance from the origin. It's always just 1, and it's going to be 1 for all of these, so they're all going to disappear, which is why I wanted to mention it now. So let me just kind of erase all of that, and instead I'm going to just write the simplified version that this is a sub n times r to the n, and I can just ignore the e to the I n theta, minus parentheses a sub 0 plus a sub 1 magnitude r plus dot 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 plus magnitude a sub n minus 1 r to the n minus 1, and then that's it. So this is what I'm left with. I've got that my polynomial p of z for any z where the radius is greater than 1 is equal to this. I haven't even used the fact that the radius is greater than 1. Any p of z is greater than or equal to this, always. You can take the biggest, essentially what we're staring at is we have the biggest degree part subtracting away all of the other crap. And if you stare at this and you think about what happens as r goes to infinity, well, what's going to happen? Well, I have positive coefficients here and here and here. I'm not using my mouse. I have positive coefficients here and here and here. These are all positive coefficients. This is a positive r. And so this is a degree n term. And this is a degree n minus 1 term. This is a degree 1 term. So r to the n rapidly outpaces r squared, r cubed, all the way up to r to the n minus 1, and 1, of course. And so it outpaces all of these, and it goes to infinity as r goes to infinity. In fact, I'm not even really sure why I made r greater than 1. I'm not sure I needed that. I don't think I did. So what we've observed is what? What we've said is that eventually the polynomial just starts to get bigger and bigger as we move farther away from the origin. Let me type that. So the conclusion here is that any polynomial will eventually just get bigger and bigger as we move farther and farther away from 0, from the origin. So as you pick bigger and bigger complex numbers, that is, complex numbers that are farther and farther away from 0, eventually you're going to reach a point where the polynomial stops doing anything weird and just starts to go in one direction, either up or down. Right? I mean, this is absolute value bars, so this could have been negative infinity easily, but the magnitude, of course, is infinity. And so what that means is that pick any number you want. Suppose we are concerned with well, let me go ahead and say it like this. Consider p of 0. This is something. It really doesn't matter what it is. Magnitude p of 0. By what we've shown, there is an r such that for any r prime, for any z equals r prime e to the I theta, or with r prime greater than r, we'll always have that p of z is greater than or equal to p of 0. So basically I can pick an r such that basically, let me just draw it. There exists some radius r such that everything out here, p of anything out here, is bigger than everything in r. In the bubble. So yeah, well, what I want to do now with that is, yeah, so maybe, you know, I don't know where p of 0 is exactly. I guess p of 0 is right here. Yeah, but there's some bubble where I know I'm going to be just only bigger than p of z0. So maybe if you kind of think about this in like, it's going to be maybe a little helpful to think of these things in 2D, even though we're really concerned with polynomials over the whole complex plane. But basically, you've seen this phenomenon before that we're talking about. Here's p of 0. Maybe it's right here. There's p of 0. The polynomial is going to do all sorts of things. Maybe I could not have made that worse. It's going to do all sorts of things. It's going to go up and down. But then eventually, it's just going to go either straight down or straight up, and it's never going to quit. And I'm just saying, bound this region here. Pick this boundary here, and just make that. And this boundary here, up and down, becomes like a whole radius. Really, actually, that was the wrong boundary. I shouldn't have picked the vertical boundary. I meant to say, you know, pick this horizontal boundary. Here's the region of activity. Past that, everything is just small or big. That's kind of what I'm doing with this circle. Make it so that no matter what happens, as long as I'm outside of that boundary, I'm always bigger magnitudinally than p of 0. Hope that makes sense. This is important. Why are we doing this? We're doing this. This matters because the closed ball b bar 0r, that is to say the set of all complex numbers z such that the magnitude of z is less than or equal to r, so just the closed ball that I drew here, is a closed bounded set. I almost said compact, which it is. And so by the extreme value theorem, so by the extreme value theorem, p of z's bar has a minimum and a maximum over it, and a max over it. But then we, you know, based on all we've said, we now know that that minimum that's inside of this bubble, maybe it's right here. Maybe right here gives you, if I plug this z0 in, I'm going to call it that. Call the min, call the location of the min. That is the input that I plug in to get the min, z0. So then if I plug that in, I'm going to get the smallest thing I can get. But of course, that is the smallest thing I can get overall for the whole function, because everything outside of this bubble is going to be bigger than anything inside of it. But then, of course, z0 is the minimum globally as well. I.e., we have a z. We have a z0 such that, and I'm just going to start throwing out my standard notation. I'm just going to say for all. Hopefully people know what I mean by this. For all z in C, the magnitude of p of z is greater than or equal to the magnitude of p of z0. So we have achieved our global minimum. We have a global minimum. So we've completed part 1 of the proof. So we found a global minimum. We know we have one. And now we just need to show that it's 0. So have a global minimum. Now need to show that p of z0, the magnitude of it is equal to 0. That it can't be anything bigger than 0. So, um, okay. So as we said we were going to do, assume block, that is by way of contradiction, that it isn't, i.e. p of z0 we're going to assume is greater than 0. Now, the idea, I'm going to state the idea, is this. So here's my complex plane again, and then let's say this is z0. And obviously, I think you're starting to get the idea, you're starting to realize probably that there's no good way to draw these functions. If you have a lot of time and a lot of coloring and a lot of like colored pencils, you could probably do it in a creative way. But like, I mean, all I can really talk about is the function like mapping this to some other point in the complex plane. You know, this is what P does. It just takes a point in the complex plane to some other point in the complex plane. That's the only real way to visualize it, without doing some like hippie shit. So you're just going to have to work with it, but it is more helpful than you think to only stare at the domain. What we're going to do is we have this thing. We know that the function is minimal here, but we're going to show that by picking numbers very close to z0, that is, we're going to kind of go within some like epsilon radius of z0, we can actually get smaller. Which will be, of course, an immediate contradiction, because getting smaller means you are no longer talking about the minimum, which is what we were talking about. But we're not going to do it directly. What we're going to do, because that would be annoying, because we would have to talk. But what I want to do is I want to instead talk about like the shifted polynomial, where the minimum is at 0. So that's the first step. So for simplicity, we will focus on the shifted polynomial q of z. We're just going to do a basic pre-calculus shifting, which is p of z plus z0. And so to write that out, so I'm just shifting it, I guess, to the, it's not to the left or the right anymore. I'm moving around on this two-dimensional plane, but it's a0 plus a1 times z plus z0 plus a2 times z plus z0 squared plus dot 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 plus a n z plus z0 to the n. And so what we're going to do now is tons, just grueling amounts, you're going to just want to jump off a bridge, tons of foiling and regrouping. And reorganizing. If you FOIL all of these terms out, if you go absolutely nuts, then you can put it back into the form with new coordinates of a regular polynomial. And this gives you some a0 prime plus some a1 prime times just z plus some, because remember, z0 is a constant. So I'm just kind of writing it back into the form of a generic polynomial. Plus some a2 prime times z squared plus dot 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 plus a sub n prime z to the n. So new coefficients are what we end up with after this process. And so there's some things that we want to note about Q. So first of all, just in terms of like real polynomials, in terms of what you're used to thinking about, what I'm really doing here is like, here's some polynomial, we'll call this like f of x. And then if I kind of look at f of x plus y, for some fixed, maybe f of x plus c, with plus c in the argument, what I've done is I've kind of shifted the whole function backward. It's the same function, just kind of lagging. Now that's not exactly what I did here, but I have just but it is kind of the same principle in that I haven't changed the function. I've only moved it somewhere. In other words, the maximum is still the maximum, and the minimum is still the minimum. I haven't changed that, as you can see from this picture. The same principle applies. I'm just taking the magnitude. It's going to look something like this, right? You know, the humps are still the humps. The peaks and the valleys have not been changed. All that's been changed is the location of everything. So all that's been changed is the locations. It's basically just P but shifted. So let me go ahead and kind of start to write these observations out. Some things about G. Not G, Q. So one, this isn't really an observation. I'm just going to use bullet points. It's basically just F. It's basically just P, but shifted. The location of where everything happens has just been moved around in a predictable way. So mins and maxes are unaffected. Unaffected. Sorry, my handwriting's terrible, but you can listen to what I'm saying. So, what that means is that, so because of that, the magnitude of P of Z0 is still the global minimum for Q. And specifically, though, we can do something kind of cheeky, because we can note that P of Z0, the magnitude of P of Z0, well, how do I write that in terms of Q? Q is just P of Z plus Z0. So if I plug in 0 for Q, then I just get P of Z0. So this is equal to the magnitude of Q of 0, which is exactly what the intention is with Q. In other words, all I've done with Q is I've shifted the location of the global minimum to 0, because that's going to be simpler to talk about. And even better, though, what is Q of A0? What is Q of 0? Well, if I stare at it, if I say Q of 0, then if I plug in 0 for that, this term goes away. You know, this term goes away. All these terms except for this one go away at Q equals 0. So what's fun is that Q of 0 is specifically the magnitude of A0 prime. And so this actually is, this A0 prime here is our global minimum. It's P of Z0's guy. So specifically then, A0 prime, by our assumption that we're trying to contradict, is greater than 0, since it equals P of Z0. And we're assuming that's greater than 0. So we actually have two terms now that are unaffected, and let's observe the other one. So Q, the first coefficient of Q is guaranteed to be non-zero by our kind of assumption that we're trying to break. But then if you stare at the last coefficient here, this A sub n here, the reason that, like, let's say this A sub 2 prime is probably different than what it was before is because for all of the coefficients passed here, you're going to get like a cubic term, right? You'll FOIL that out. You'll end up with like some stuff involving A3 and like Z0, but it'll be to the second power, and then that'll have to feed back in here. But this is the biggest guy. There's not going to be anything there's not going to be any products of foiling that come back in and change this coefficient here. It's still the same. And since f is a degree n polynomial, this is non-zero. So in fact, a sub n prime is just equal to a sub n, and that is non-zero since we're assuming that f is not f. I keep saying f when I should say p. Since we're assuming p is degree n. So let me kind of review the original plan. The original plan was to pick numbers very close to the minimum, to the location of the minimum, and show that you actually get smaller than the minimum. Well, I'm going to do the same strategy, but now my minimum is 0. So going to pick very small complex numbers. Force Q to be smaller than it's allowed to be. In other words, what I'm going to kind of prove in general is that if I have a minimum for a polynomial that is non-zero or non-zero in magnitude, then I can actually, everything nearby it is actually smaller, which makes no sense unless it's zero. That's what I'm going to show. Okay. So I want to revise things. I'm almost ready to do the real math here. I want to do one more thing. So I have that Q of z is equal to a0 prime plus a, getting ahead of myself, a1 prime z plus a2 prime z squared plus dot 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 plus an prime z to the n. I know that this is non-zero. I know that this is non-zero. Any of these other guys could be zero. And I don't want to, what I'm really going to care about the most is the highest degree z term here that's non-zero. So I'm going to say pick k greater than 1 to be smallest non-zero ak, a term, to be the index of the smallest non-zero a term besides a1. So in other words, maybe this is 0, maybe this is 0, maybe this is only the third one that's non-zero. Then I'm just going to write instead a0 prime plus a3 prime z cubed, right? I don't know if that's what it is, but that's what I'm going to write down. I'm just going to write plus a sub k prime z to the k plus a sub k plus 1 prime z to the k plus 1 plus dot 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 plus a sub n prime z to the n. So I just needed to do that to kind of make things look nice. Actually, no, it's not just to make things look nice. This k is an important. This k is going to be important. So now is the part where you're an analyst. You do a bunch of garbage, and then you're like, how do I finagle this to be as small as I want it to be? And then you pick some numbers that make it as small as you want it to be, that you can see in hindsight, and then you just pretend to your students that you knew all in advance. So you state, the magic numbers, and everybody's just mystified, and then they're like, oh, that's why you picked it. It's a stupid magic trick. It's how you have to teach this shit, all right? It's not. I don't make the rules. So I'm going to define some things that will seem completely random here. Specifically, I'm going to say I'm going to say capital A is equal to the magnitude of all of the terms past these first two. So it's going to be the magnitude of a sub k plus 1 prime plus, and that's closed brackets too. This has already been triangle inequalitied. Plus a sub k plus 2 prime magnitude plus dot 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 plus magnitude a sub n prime. And this is greater than 0 because, at the very least, a sub n prime is greater than 0 because it's equal to a sub n. So that's greater than 0, and because it's greater than 0, I can put it in the denominator. So I'm going to want to consider so basically what I'm going to do is I'm going to say pick L, some real number L, positive, so that a sub k, the magnitude of a sub k, the actual first term that I do care about, divided by a, and then also divided by L, is less than 1. And then I'm going to say, let epsilon be less than that. So this is a number, it's a function of the polynomial, and I'm going to make epsilon less than that. This is going to be the radius that is small enough. This is going to be the radius that will always give you your contradiction. Okay. So consider the complex number epsilon e to the I theta. We'll choose a specific theta in a minute. But that's what we've got. So we've got our epsilon defined. So just to kind of go back to this picture, right? We've got, actually I should just draw a new picture because we're at 0 anyway. So this is 0. I don't know really see the point of having a full-on graph. And then we've defined our radius now. That's epsilon. And so we've got our point here, you know. Well, it's not really epsilon. It's more you know, it's a sub k over LA is this radius. But then we've got some point in here, epsilon e to the I theta. And it's inside this bubble. And we're going to show that if you plug this guy into the polynomial, then you get problems. Okay. So then Q evaluated at epsilon e to the I theta is equal to, let's just write it out, a0 prime plus a sub k prime epsilon to the k e to the I k theta. And then I'm going to just do the dots at this point, and then plus the last one, which is a sub n epsilon to the n e to the I n theta. So here's the thing evaluated correctly. And what we're going to do is, what we're going to focus on first is just these two. Focus for now, I cannot write in this blue. So focus on these two. And in fact, what I'm going to basically say is this is how we're going to pick our theta. And this is a little confusing. I'm going to have to draw more circles. You're starting to realize at this point that complex analysis is just basically just drawing circles forever. So my claim is this. I'm just going to go ahead and say this claim. The absolute value of this, so claim, we can pick a theta such that the absolute value of these first two terms, a0 prime plus a sub k prime epsilon to the k e to the I k theta, is less than or equal to the difference between a sub 0 prime minus a sub k prime epsilon to the k. Now this is a confusing thing to look at. Don't worry, it's not that complicated really. What you've got here, remember, a sub 0 prime and this whatever garbage mess, these are just complex numbers. So what we can do here is we can remember some vector addition stuff. And that's really all you need in order to see this. And you also got to remember that what I've really got with a sub k prime epsilon to the k e to the I k theta is I've got a parameter theta that I can control, right? So I'm going to draw a circle here. And specifically what this circle is that my complex number is like right here, let's say. Or maybe let's say like right here. And what I mean by this is that this right here, this is a sub k prime epsilon to the k e to the I k theta. So maybe that's my point. And the reason I drew the circle is by changing theta, I can move around the circle. So as I increase theta, I'm going to go like this, around and around and around. It's not a perfect circle, I don't think, because a to the k, a sub k is not, you know, unless the complex. I think this is an ellipse, but it doesn't matter. It really doesn't matter at all. Actually, it does. I can't say. Okay, well, it would have mattered if I wrote down the thing I meant to write. I meant to write equals here. But I don't think it was actually correct to write equals. I can only say less than. But let's just assume it's a circle so I can show you the equals part because I think that's simpler. A sub k prime, let's just say that's like, wait, a sub 0 prime, excuse me. Let's say a sub 0 prime is like right here. Actually, let's say it's like, I think I made the circle too big. Let's say it's like right here. And so the vector sum of these two guys is what? Well, to do vector summation, you just draw from one to the other, or you draw from 0 to the first guy, it doesn't matter which one, and then you draw kind of in the, you kind of think about this, but happening parallel from it. So you cut this kind of parallel point, and so this is the sum. I don't have room to write it, so it's the sum of the two. So this is the new complex number. This right here, this is the thing I'm taking the magnitude of in the brackets. And you can see what's going to happen. As I change theta, this sum is going to change. And so what I'm going to do is I'm going to pick theta specifically to put it right here, just completely antagonistic to this a sub 0 prime. So pick theta such that to be totally opposite, totally opposed to a 0 prime. And then if I do the vector summation, well, I go all the way out to here, and then I go all the way back, or as far back as I would need to get to a. Maybe I end up just here. But the bottom line is, you know, the precise distance I've gone is this right here at that point. A sub 0 prime, that is the length from here to here, minus the distance that was lost going from here to here. And so if I just pick this theta so that I end up like kind of parallel on the same like line as if the line spanned by a 0 prime, then I get this. Now if this is not, if this complex number does not give me a circle but instead gives me an ellipse, then I can still get on the same kind of level as that. I just might be further up, right? And so in that case I would end up less than that. And so I can only say less than or equal to, but I can still pick it uniquely in the exact same way. So there's just some geometry arguments that I had to make, but that's the theta we want to pick. We want to pick theta such that this guy is less than this guy. And I hope I've convinced you that we can do that, and so now we will have done that. And now we're ready to party, I think. I think now we're at the kind of tail end of the proof. That was the hardest part. So, what have we got? Let's go ahead and just like put that bars around it. We've got that Q evaluated at epsilon e to the I theta. This is less than or equal to the magnitude of wait, why am I saying? Yeah, I'm dumb. It's just equals. Getting too reliant on my notes here. I'm getting tired. A 0 prime plus a sub k prime. I know I have this up here. I'm just writing it down here. Epsilon to the k e to the I k theta plus dot 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 plus a sub n e epsilon to the n e to the I n theta bar. And so now I'm going to use the triangle inequality and just take these first two terms out and then look at the rest of it as the rest of it. So this is less than or equal to a sub 0 prime plus a sub k prime epsilon to the k e to the I k theta plus absolute value of the rest of it. So that would be a sub k plus 1 prime epsilon to the k plus 1 e to the I k plus 1 theta plus dot 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 plus a sub n epsilon to the n e to the I n theta. Promise we're almost done with this part. And of course, I can replace this thing in brackets with the thing I just wrote here, and I will. But before I do that, I am going to do that, but I'm also going to use the triangle inequality one more time on this term here, so break up those terms. So I'm going to, this is less than or equal to, both of these terms I'm going to replace with something less than or equal to them. I'm going to say less than or equal to the thing that I argued earlier, a sub 0 prime minus, brackets around it, minus a sub k prime epsilon to the k, plus, and then I'll put brackets here. This is going to be magnitude a sub k plus 1 prime, epsilon to the k plus 1, and then this term, these terms are, these e to the I terms are all just 1, just like before. And then I get absolute value a sub n, epsilon to the n, and then that's closed, and that's that. Okay. And now I can make one last observation that's kind of cheeky. Actually, this is not the last observation that's kind of cheeky, but I mean, so epsilon, I specifically made sure that it was less than 1, right? I specifically picked this L here to make sure that this thing here that I was setting epsilon less than is less than 1. And so since epsilon is less than 1, if I take epsilon to bigger and bigger powers, I'm going to get smaller and smaller numbers. So observe that epsilon to the k plus 1 is greater than epsilon to the k plus 2, is greater than epsilon to the k plus 3, etc. In other words, if I took, I can basically say less than or equal here, and replace, I could say basically replace all these epsilons in here, all the epsilon to the stuffs, with epsilon to the k plus 1, then factor it out. So that's what I'm going to do in this next step. And so this is less than or equal to a sub 0 prime minus absolute value a sub k prime epsilon to the k plus epsilon to the k plus 1 parentheses a sub k plus 1 prime plus dot 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 plus a sub n prime. And at this point, everybody watching this video just has no clue what's going on anymore. But if you were really paying attention, you would be like, whoa, what the hell? What's this thing? Oh, wait. This thing is A. We defined it earlier. There it is. Okay, so there's A. So this whole thing is just A. And I'm going to pull out an epsilon as well. So this is equal to a 0 prime minus a k prime epsilon to the k plus epsilon to the k times epsilon times a. Okay, well, what's epsilon times a? Epsilon times a, I don't know what it is, but it's certainly less than what epsilon is less than. And epsilon is less than the magnitude of a sub k prime over a times L, right? Is that what I said? Yeah. So epsilon is less than that, so I'm going to go ahead and say less than. And so at that point, I have epsilon a. Oh, wait. There's an a here too, and then the a's will cancel. So that was the point of putting a in the denominator there. And I'm also going to write, I'm going to force the common denominator while I'm at it here. I'm going to say this is less than a0 prime minus not just a sub k prime, I'm going to say L over L, a k prime in preparation for the final hour. And then this is plus epsilon to the k, I still have one of those, times, what do I have left? I just have absolute value a sub k prime over L. And so what I have here is I can pull out the epsilon to the k, a sub k prime that's in both these terms, and this is equal to a sub 0 prime minus L minus 1 over L times a sub k prime times epsilon to the k. Okay. Now, what's important about this? What's important about this is the thing that I haven't said this whole time, the key, which is, there's two things to observe. One, is that this thing is greater than 0. And so this whole thing and so I'm subtracting something off. So I'm subtracting something positive off from this, and so it's smaller. And so this is less than or equal to just if I put a0 prime here by itself. Now, what is a0 prime? This is the punchline. I mentioned this guy before. We talked about him. a0 prime where is it? a0 prime is equal to p of z0. It's the minimum. Or rather, if you'd rather, it's q of 0. It's all those things. And that's supposed to be and so what have I just said? I've just said, so the magnitude of q of epsilon e to the I theta is strictly less than, this one here, right here, is strictly less than a sub 0 prime. Which, not a sub 0 prime, I shouldn't say that. It's q of 0. And that is problematic because this is supposed to be the minimum, i.e. it is less than the min. And that's it. That's the contradiction. So, conclusion. The magnitude of p of z0, which is equal to the magnitude of q of 0, is equal to 0. Because if you pick it to be bigger than 0, then I can show you a little bubble where if you picked a complex number in that bubble, you'd actually get smaller than it, contradicting that it is a minimum. And so that proves that every so what have we proven? So we've proven that every degree n polynomial has a root. It has a thing I can plug in to get 0. We still need to do the whole factoring thing, but that's really easy. So and it just kind of relies on induction. Kind of. It's kind of a trivial induction. So consider, so this is part 3 of the plan that I mentioned before. So consider p of z is equal to a0 plus a1z plus a2z squared plus dot 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 plus an z to the n. So here's our polynomial. By what we've shown, p of z has a root. I'm going to call it z1. So p of z1 is equal to 0, but it's also equal to, if I plugged it in here, it's equal to a0 plus a1z1 plus a2z1 squared plus dot 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 plus a2 or an z2 to the n. So if I say, so then p of z is equal to, of course, p of z minus 0, which is, I'm sure most of you can just finish this at this point. This is p of z minus p of z1, which is equal to, and if I just kind of group everything together, what I get is a0 minus a0, so that's just 0, plus a1z minus a1z1 plus a2z minus, a2z squared minus a2z1 squared. You see where this is going. Plus dot 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 plus a sub n z to the n minus a sub n z to the n, or z1 to the n. And if I group everything out, I get that this is 0. And then I also get a1z minus z1 here plus a2 z wait, am I a hack? Oh no, I'm fine. Wait, what? Wait, hold on. Ooh, I did a mistake. I mean, it's not that big a deal, but it isn't as simple as I thought. Actually, it doesn't really matter. The bottom line... Okay, it seems like I need some kind of binomial theorem here now. I made a mistake in my notes. In my notes, I just wrote this. I did the classic. I wrote this as just z minus z1 squared, but it's not z minus z1 squared. It's z squared minus z1 squared, which is not the same thing. Z minus z1 times z plus z1, and you can always do that, but that's going to be annoying. You can always do that, but what about the third one? Difference of cubes? Hold on. Well, shit, I need to fix that. How can I fix that? I'm gonna have to cop out on this one. It's 1 a.m. It's plus dot dot dot. I might make a follow-up video or something. And I'm just gonna say like stuff z minus z1 to the n. It's in principle this is right, you know. In principle, you factor out the z minus z1, all right, and then what you get is a polynomial of one less degree. That's the punchline. Is that the constant ones cancel out, and then you get other stuff. It doesn't directly go to this because I'm a moron, but you can still factor it out at the end because the constants have factored out, and you get z minus z1 times another polynomial, but it's a new polynomial, and it's of degree n minus 1, and then you apply it again. Apply the result again. You know, get z minus z1 times z minus z2 times a polynomial of degree n minus 2, and then dot dot dot, right? And so that's why it's important to mention that multiplicity thing, because there's no guarantee that these z's that I'm pulling out aren't the same as some previous ones. But it is kind of n distinct roots just in the way that I kind of extract that information, right? I don't know what I'm going to pull out, but I am going to pull out n things. And so that's it. That is the whole thing. So aside from this, ignore this. I mean, you can factor it yourself. I just don't remember offhand how to factor a cubed minus b cubed and pull out an a minus b. I know you can. You'd have to do some polynomial long division, and I don't feel like doing that, so not going to do that. You can do that. Find a general formula for that, and then pull it all out. But it'll work. It'll work, I promise. And so that does it. So that completes the proof of the fundamental theorem of algebra. It is it's pretty involved. There's a lot going. I mean, I think it's a really good thing to try to understand. It's a really good transition to more complex proofs that have a lot of legwork involved in them. You know, most complex math proofs are like, they're annoying to get through, but there's always a bunch of little nuggets and like pieces of information that are valuable once you actually like understand them. But you have to kind of like wade through it and find the juicy bits as you go. So anyway, hope you enjoyed that, and cheers.